let's talk about fire and smoke detection, and the first thing we want to talk about is carbon monoxide detectors. Now, carbon monoxide detectors are found very often in the cockpit or the cabin of an aircraft, and the reason for that is that the cabin heaters on small aircraft are basically heat exchangers around the exhaust of the aircraft, and if they get a leak in them, you can end up with carbon monoxide in the aircraft cabin, which is a bad thing, and so some aircraft will have carbon monoxide detectors in the cockpit or the cabin. Now, if you're using a portable carbon monoxide detector checking for carbon monoxide, you can tell when air samples do contain carbon monoxide because the yellow silica gel will turn green. And the FAA will ask you, what color is that yellow silica gel going to turn when the air samples do contain carbon monoxide? And the answer is they're going to turn green. Now, if a carbon monoxide portable test unit has been contaminated with carbon monoxide, you can return that unit to service just by installing a new indicating element. Now let's talk about smoke detection systems, and first of all, a photoelectric cell. Smoke detector instruments are classified by their method of detection. And on a photoelectric cell, the method of detection that you're using is a measure of light transmissibility in the air, and so that becomes a photoelectric device. And basically what happens with a photoelectric cell is that you've got a lamp shining a light out, and if there's no smoke moving through the unit, that light will just go from one side to a receiver on the other side of the unit. But if there's smoke in the air, or possibly some other contaminant like dust or something like that, it will scatter and refract the light, and it will refract the light into the sensor, which will tell you then that you have smoke moving through that unit. Although it can be confused not just by smoke but by dust and other contaminants in the air. Photoelectric cells like this are commonly used to detect smoke in the cargo and or the baggage compartments of an aircraft, areas where people aren't visually looking into that area all the time. Now, a photoelectric smoke detector will warn you when smoke is present, but it will not tell you if you've got a heat rise, like when you've got a fire that's starting but does not have any smoke. Another type of smoke detector is a visual smoke detector. A visual smoke detector like this is activated by the smoke moving through, which turns on lamps inside the smoke detector. On the smoke detector, the green lights basically just tell you that the system is on and operating, and then if smoke moves through the unit, the smoke will activate lights which turn on and illuminate these windows, and that way you know that you do have smoke. And that simply is a visual type as opposed to a photoelectric smoke detector. Now let's talk about fire detection systems. With fire detection systems, very often they use a bimetallic thermal switch. Here's our bimetallic thermal switch, and it's a heat-sensitive switch, and what the bimetallic thermal switch does is it completes a circuit at a certain temperature. So the bimetallic thermal switch completes a circuit at a certain temperature. Thermal switches that are used in a fire detection system that has a single indicator light, those thermal switches will be wired in parallel with each other, but in series with the light, in parallel with each other, in series with the light, so that any one of the switches that does sense a fire can turn on that indicator light. Now, the Fenwal fire detection system uses spot detectors that are wired in parallel between two separate circuits. You've got two separate circuits here, And the reason those spot detectors are wired in parallel between those two separate circuits is so that if you get a short, you can have a short in either circuit, either one of those circuits, without causing a false fire warning. And that is an advantage of the Finwall spot detector fire detection system because of the fact that it does have the two separate circuits. Now, another way to detect fires is through a thermocouple fire detection system. What happens when you have a thermocouple system is that you have a number of active sensors and you have a reference sensor. The thermocouple fire detection system measures temperature rise or rate of temperature rise compared to a reference temperature. The active sensors will be in the area of the engine where a fire might possibly start. The reference sensor is an area where you would not expect to have it start. And if you do get a fire going, what happens is one or more of these active thermocouple sensors will sense a hotter temperature, and the temperature difference between the active and the reference units will generate a small current. And so when these active sensors are heated and there is a temperature difference between that and the reference, it generates a current, and that in turn activates the fire warning system, the thermocouple fire detection system. Now, another type of fire detection system is a continuous loop fire detection system. And with a continuous loop, what you've got is basically what the name says, continuous loop of sensor that goes around those parts of the engines that are susceptible to fires and that you want to make sure are protected. The most common cause of false fire warnings in a continuous loop system like this is if the sensors get dents in them or kinks in them or they get crushed. And so when you're working around the engine, you have to be very careful to not create, to crush the sensors or to create dents or kinks in those sensors, because that will in turn create false fire warnings. The maintenance of fire detection systems on aircraft includes the replacement of any damaged sensing elements that are damaged enough to create problems. Now let's move to the interior of the aircraft and assume that you've detected a fire. What are you going to use to put it out? There are 4 basic types of fire extinguishing agents that you would use for aircraft interior fires. And those 4 agents are water, carbon dioxide, dry chemical, or halogenated hydrocarbons, commonly known as halon. Now, the problem with some of these is that if you're in an interior of an aircraft, there may be people in there, and you don't want to suffocate the people in the process of putting the fire out. So you want to use the least toxic fire extinguishing agent that you can. And the fire extinguishing agent that is considered to be the least toxic is halon 1301. Halon 1301, and on the test you will see it both ways by halon 1301 and its full fancy name, bromo trifluoromethane. But don't worry about having to remember bromo trifluoromethane, because whenever you see that on the test, immediately after it you will also see halon 1301. The advantage of halon 1301 is the concentrations that you need to have it in to put out a fire are very, very low, which makes it better even than carbon dioxide, because you need a big concentration of carbon dioxide to put out a fire. So the least toxic fire extinguishing agent, and the one you would use for an interior fire, is halon 1301. Now, a CO2 or carbon dioxide handheld fire extinguisher can be used on an electrical fire, but only if the horn here is non-metallic. You would not want to use one with a metallic horn if you had an electrical fire. So only if the horn on it is non-metallic can you use that CO2 handheld extinguisher on an electrical fire. Now, on large aircraft like this, it's not at all uncommon to have break fires on the aircraft. And the appropriate extinguishing agent to use if you have an aircraft break fire is dry powder chemical. Dry powder chemical is what you would want to use on a break fire. Now, as you get into bigger aircraft, they typically have built-in fire extinguishing systems, particularly to address any fire that might occur in the engine area. For instance, these are the fire extinguishing bottles for the engines in a Cessna Citation. Now, what are these bottles normally charged with? Typically, they would be charged with halogenated hydrocarbons, that's halon, and with nitrogen. They would not be charged with carbon dioxide or sodium bicarbonate. The halogenated hydrocarbons, the halon, is the fire extinguishing agent, and the nitrogen is the propellant that gets it out there and distributed through the engine. Now, when you're looking at those fire extinguisher bottles, if a fire extinguisher cartridge has been removed from the discharge valve for any reason, it is strongly recommended that the cartridge be reused only on the original discharge valve assembly. And the reason for that is that the cartridge is not going to fit quite right on any other bottle because of the wear that it's had on it, and so you only want to use it on the original discharge valve assembly, or else it's not going to fit properly for the discharge. Now, in a fire protection system like this, you have a squib, and the squib is the device that causes the fire extinguishing agent to be released. And basically, the squib is the explosive device that breaks open the exit way so that that fire extinguishing agent, which is under pressure, can push its way out and be released into whatever area you need to put the fire out in, whether it's the engine or some other area that's protected by this agent. As a safety precaution, during removal or installation of the discharge cartridges, the terminals of the discharge cartridges should be grounded or shorted. It would be bad news if that thing went off when you were handling it. So before connecting the cartridge terminals to the electrical system, the system should be checked with a voltmeter to make sure that no voltage exists at the terminal connections. There are two colored discs on the outside of the airplane that tell you about whether the extinguishing agent has been discharged and whether it was done intentionally or whether it's had a thermal discharge. If it has been intentionally discharged, the yellow disc, which is located on the outside of the fuselage, will be blown out. So one of the things that happens is when you intentionally discharge the fire extinguishing bottles, as part of that intentional discharge, it blows out, the pressure blows out the yellow indicating disc on the outside of the fuselage. So if the yellow disc is missing, it means that that system has been intentionally discharged in order to put out a fire. On the other hand, for each of these fire extinguishing bottles, each one has its own red indicating disc that will tell you if there has been a thermal discharge, meaning an overpressure discharge of a built-in fire extinguisher system. If either one of these bottles overpressurizes because of excessive heat or whatever, it will blow out its own red disc, and that tells you that there was a thermal discharge of that built-in fire extinguishing system. Now, a fire extinguishing system that has been discharged, if it uses a Freon agent, the maintenance that you have to do on it, if it's been discharged, is you purge the system with air, and then what you need to do is replace the container. You purge the system with air and replace the container. And by the way, you need to know that fire extinguisher lines are color-coded brown. Fire extinguisher lines are color-coded brown. Now, you can check the containers to determine its charge, and one way to do that is by weighing the container and its contents. So by weighing it, you can tell how much of a charge it's got in it. The fire extinguisher container should be replaced if they're pressure checked and found to not be between the minimum and maximum limits. There are minimum and maximum pressure limits depending on temperature that the containers can have, and if it's not within those limits, it needs to be replaced. To determine the allowable pressure and temperature range for a fire extinguisher, what you do is use the container pressure versus temperature chart. So take a look in Appendix 2 at Figure 21. And when you get to Figure 21, sure enough, the label on the chart says container pressure versus temperature. It's got 3 columns on it. The left-hand column is temperature in degrees Fahrenheit. The center column is minimum container pressure, and the right-hand column is maximum container pressure, and that's in PSIG, pounds per square inch, on the gauge. So the FAA might give you this chart and ask you, what is the temperature range for a fire extinguishing agent storage container that has a pressure of 330 PSIG? And they want us to consider the 330 to be both maximum and minimum pressure. Same pressure indication, 330. So let's take a look at maximum first of all. That's the right-hand column in the chart. And we come down that column looking for 330 PSIG, and son of a gun, do you suppose we find it? No, of course not. What we do find is 317 and 342, but no 330. So what we're going to have to do is interpolate. And in order to do that, we need to find the temperatures at each of those pressures. So coming across to the left-hand column, which is for temperature, at 317 PSIG, the temperature would be 40 degrees Fahrenheit. At 342, the temperature would be 50 degrees Fahrenheit. And now what we have to do is to interpolate. So let's take a look at the numbers at how this starts out. First of all, at 317 pounds per square inch, the temperature could be 40 degrees. At 342 pounds per square inch, the temperature could be 50 degrees. But the pressure they're allowing us is neither one of those. It's 330, which is somewhere between 317 and 342. And what we need to find out is what is the allowable temperature, and it's going to be somewhere between 40 degrees and 50 degrees. So what we basically have to do is work a ratio problem and figure out how that's going to set up. So here's what the numbers are going to look like. We're trying to get somewhere between 50 degrees and 40 degrees, and we'll set up the proportion. The question mark represents the temperature that we're trying to find, a temperature that is equivalent to 330 PSIG. So we have an unknown temperature, minus 40 degrees, divided by 50 degrees minus 40 degrees. What that's going to do is set up the ratio so we know how far between 40 and 50 degrees we're going. And that's going to be equal to 330, which is the pressure the FAA has given us, 330 minus 317 divided by 342 minus 317. And this is going to give us the ratio so that we can figure out what our temperature is going to be. Okay, when we start reducing that down, 50 degrees minus 40 degrees is 10 degrees. So we've got 10 degrees on the bottom of our formula here. We still don't know yet what our temperature is, so that stays in as a question mark, minus 40 degrees. 330 minus 317 PSIG is 13. 342 minus 317 is 25. So basically what we're doing is looking for a temperature that has the same relationship between 40 and 50 degrees that our pressure of 330 had between 317 and 342. And the ratio on the pressure is 13 over 25. We're 13/25 of the way between 317 and 342. And we're going to use that 13/25 to figure out what our temperature needs to be over here. So let's take a look at the next step and see how that comes out. We don't know for sure what our temperature is, less than 40 degrees, but we know that we had 10 degrees, the difference between 50 and 40 degrees. So 10 degrees times 13 divided by 25 gives us a temperature increment of 5.2 degrees. And we're working this all in degrees Fahrenheit. So the temperature we're looking for is 5.2 degrees plus 40 degrees, which was our lower temperature. And 40 degrees plus 5.2 degrees means that our temperature is 45.2 degrees. 45.2 degrees or 45 degrees is our allowable temperature at this maximum pressure. That's half the problem. Next, we need to determine the allowable temperature at minimum pressure of 330 psig. So we take a look at the column for minimum container pressure, and we go down it looking for 330 psig. And son of a gun, of course, what happens again? It's not there. What we do have is 319 and 356. So again, we're going to have to do some interpolation. But first we need to take a look to the left at the column for the temperature. If the minimum container pressure were 319 psig, the allowable temperature would be 70 degrees Fahrenheit. If it were 356 psig, the allowable temperature would be 80 degrees Fahrenheit. Well, 330 is between there, so we know that our temperature is going to be between 70 and 80 degrees Fahrenheit, but now we need to interpolate again. Let's take a look at how the numbers set up. At a minimum pressure of 319, our allowable temperature is 70 degrees. At a minimum pressure of 356, our allowable temperature is 80 degrees. The FAA says that our minimum pressure is 330 psig, and that's between 319 and 356. So our temperature, which we don't know yet, it's shown by the question mark, is going to be somewhere between 70 degrees and 80 degrees. And again, we want to set up our formula in order to figure out the ratio on that. And the numbers look like this. The question mark is the temperature we're trying to find. It's between 70 degrees and 80 degrees. The pressure we're allowed is 330. 330 is between 319 and 356 on the pressure. So the difference between 330 and 319 is 11 pounds. The difference between 356 and 319 is 37 pounds. So the pressure of 330 is 11/37ths of the way between 319 and 356, 11/37ths of the way. So our temperature is also going to be 11/37ths of the way between 70 degrees and 80 degrees. And the way we determine it exactly is the difference between 80 degrees and 70 degrees is 10 degrees. And so our formula is laid out of our unknown temperature minus 70 degrees divided by 10 degrees will be the same as 11 divided by 37. 11/37ths of the way between 70 degrees and 80 degrees. And working on through the formula, here's what it looks like next. 10 degrees times 11 divided by 37 gives us 3 degrees Fahrenheit. And we add that 3 degrees Fahrenheit to the lower temperature of 70 degrees. 3 degrees plus 70 degrees means that our temperature is 73 degrees. So the acceptable temperature range is from 45 degrees to 73 degrees. The acceptable temperature range that we can have given both a maximum and minimum pressure of 330 psig is between 45 and 73 degrees Fahrenheit. Take a look again back at figure 21, because this time the FAA is going to ask you a question, but in the opposite direction. This time what they're going to do with the container pressure versus temperature chart is they're going to give you the temperature and they're going to ask you what is the acceptable minimum and maximum container pressure. What they're going to tell you is the surrounding area temperature is 33 degrees Fahrenheit, and they're going to ask you what pressure is acceptable. So the first thing you do is you start down the temperature column and you're looking for 33 degrees Fahrenheit. Are you going to find it? Of course, you're not going to find it. What you find is 30 degrees and you find 40 degrees, but 33 is not there. So guess what we're going to have to do? We're going to have to interpolate. So let's take a look at the center column, which is the column for the minimum container pressure. If the temperature were 30 degrees, then the container pressure allowable would be 209 psig. If the temperature were 40 degrees, the allowable minimum pressure would be 230 psig. The temperature is 33 degrees, and that means we know that the minimum allowable pressure will be between 209 and 230 psig. So what we have to do then is interpolate with those numbers. The unknown that we're trying to find out this time is the allowable pressure at 33 degrees Fahrenheit. At 209 pounds per square inch is what we're going to get at 30 degrees. At 40 degrees, we're going to get 230 psig, and we want to get a ratio between them in order to find out how much the pressure will be allowed to be at 33 degrees Fahrenheit. And basically, just eyeballing it, it looks like it's going to be about 3/10 of the way. But let's go ahead and work through the numbers, and here's how those numbers set up. First of all, our unknown is what the pressure can be at a temperature of 33 degrees. And we're going to work a ratio problem. The difference between 30 and 33 degrees is 3 degrees. The difference between 30 and 40 degrees is 10 degrees. So basically, we're looking for a pressure that is 3/10 of the way between 209 and 230. Now, the difference between 209 and 230 is 21 psi. So what we're looking for is a pressure that is 3/10 of the way between 230 and 209, and in order to do that, we just keep working on through our formula, and what happens next then is that we get 21 times 3 divided by 10, and that gives us 6.3 psi. And we add that 6.3 psi to the smaller pressure, 209, and that gives us an allowable pressure at 33 degrees of 215.3. And we could probably round that off and call it 215. 215 psig is the allowable minimum temperature, allowable minimum pressure at a temperature of 33 degrees. Allowable minimum pressure at a temperature of 33 degrees. Well, we already know that we don't have a temperature of 33 degrees Fahrenheit in our temperature column. We found our temperatures of 30 degrees and 40 degrees Fahrenheit. So this time all we do is go to the far right-hand column, which is our column for maximum allowable pressure. And at 30 degrees Fahrenheit, the maximum allowable pressure would be 295 psig. And at 40 degrees Fahrenheit, the maximum allowable pressure would be 317. So at 33 degrees Fahrenheit, we know that the number we're looking for, the pressure we're looking for, is somewhere between 295 and 317 psig. So what we have to do is interpolate. At 30 degrees, the maximum pressure is 295. At 40 degrees, the maximum pressure is 317, but our actual temperature is 33 degrees, and we're trying to find out what the allowable maximum pressure would be at 33 degrees. So we set up our ratio to figure out how we're going to do this interpolation. And again, we're trying to go between 317 and 295 on the pressure, the same distance that the 33 degrees is on the temperature. The difference between 30 degrees and 33 degrees is 3 degrees. Between 30 degrees and 40 degrees is 10 degrees. So we want to be 3/10 of the way between 295 and 317. The difference between 317 and 295 is 22 psi. And we want to take 3/10 of that 22 and we want to add it then to the 295. So let's take 3/10 of that 22. 3/10 of that 22 is 6.6 psi. 6.6 psi, and we add it to that lower pressure, 295. 295 plus 6.6 is 301.6 psig. So at 33 degrees, the maximum pressure that we could have is 301.6, and I'd say we could round that off to 302. So the acceptable pressure range, if you're given a temperature of 33 degrees Fahrenheit, the acceptable pressure range is a minimum of 215 psig to a maximum of 302 psig.